right, so far we've talked about heat, which is energy, heat transfer, which is how energy transfers from a surroundings to a system or vice versa. We have done heat calculations, the heat change in energy at least. We call it the heat Q, and the change in energy is the Q is equal to MCAT, mass, times specific heat, which is how much energy something will absorb in order to change its temperature, times that temperature change. All right, and we did coffee cup calorimetry, where we figured out if we put something into another substance and one temperature went down, the other temperature would go up, and we could use that to calculate specific heat of a metal. So today we're going to talk about how do you do that with a chemical reaction. Because yes, I could go and get my coffee cup and I could put a chemical reaction in there and take the temperature, but we're using water to show the temperature change because water is such a good absorber of energy. So today we're going to introduce the idea of the bomb calorimeter. Now, when I was in high school, we thought this name, bomb calorimeter, was hysterically funny. And all we wanted to do was put a ham sandwich in a bomb calorimeter to figure out how many calories. Because essentially, that's what you're doing with a bomb calorimeter. You're calculating the energy that something has. In the picture here, this is out of the Mastering Chemistry online stuff. If you've noticed, when you've worked a problem, over in the left-hand corner, there's a little thing and it'll say something about page numbers. Doesn't always get you to the right page, but you can move through and find what you're looking for. At least get you to the right section. So what a bomb calorimeter is you have a chamber in which you have a place to put a chemical. And you've got, in this case, we've got a chemical and we've got oxygen in the chamber, so we can then react that, get some combustion going, react that equation, or that chemical. I don't know what is wrong with me. Well, we all know it's COVID. I don't have it. Don't worry. Okay. Notice that this chamber is attached to wires. Those are ignition wires. And then we have a bunch of water surrounding it inside of a big tank. Okay? Now, I've actually used one of these. That's part of physical chemistry. And we actually put a little bit of substance inside, and there's actually a switch that you push, and the electricity goes through, and basically it ignites. In this case, it's going to ignite the oxygen in the little interior tank, and it's going to cause that substance to burn. So that's, like I said, when we were in high school, we wanted to put a ham sandwich in one and electrocute it and cause it to burn and calculate the energy given off. Why a ham sandwich out of all the things we could put in there? I don't know, but my class was stuck on ham sandwiches. So the bomb calorimeter is great because let's use a new color today. Q of the calorimeter is going to be equal to the Q of the reaction. That's negative, because if one's positive, the other's going to be negative. If the energy is being released by the reaction, the bomb calorimeter is going to gain the energy. So that's the simple equation we're using here. Now, the other information we're going to get in these problems is our substance. So we're going to have a mass of substance and the temperature change of the water. And we're also going to have a heat capacity of our calorimeter. Okay? So just like a metal has a heat capacity, calorimeters have a heat capacity as well. Okay. Here's our first example. We have 1.010 grams of sucrose. So here is my chamber. I have 1.010 grams of sucrose. Sucrose, that's table sugar, C12H22O11, and I have this calculated, the molar mass of that, because we are going to have to change it to moles, 342.3 grams per mole. Okay? And we have our big tank of water, and we have our ignition. The reaction occurs. We discover that the specific heat of the calorimeter is 4.90 kilojoules per degree Celsius. So the first thing we have to do is figure out the energy of the calorimeter. So we're going to take the energy of the calorimeter is going to be equal to the specific heat of the calorimeter times the temperature change. The temperature change was 28.33 to 24.92. And the calorimeter value is 4.90 kilojoules per degree Celsius. Our Celsius cancels, and we're going to go through and multiply that out. And here I'll do that on my calculator here. So we have, I've already forgotten what the numbers were. We have 4.90 times, and it's 28.33 minus 24.92. I should have done that first. 28.33 minus 24.92. There's your temperature change, delta T. And we're going to multiply that by the heat of reaction, the specific heat of the bomb calorimeter, 4.90. And we get 16.709. That is not what I wanted. 16.709. For our calorimeter. Now I'm going to erase my picture so that I have some more room. Now, we know that the heat of the calorimeter is equal to the heat of the reaction, only the reaction was given off, so the heat was given off, so it's negative. All right, this value is for 1 mole. Did we have, in fact, 1 mole? No, we didn't. We had 16.709 kilojoules, and the amount we had was 1.010 grams. How do I change grams to moles? Go to the mole map, grams to moles, divide by the molar mass, 342.3 grams per mole. So now we're going to take 16.709 divided by, and I'll do my math again, 1.010 divided by 342, okay, 0.00295. So if, I'm not going to pull the calculator up again, you're just going to have to trust me. I get 5,664 kilojoules. Okay, if we want to write that in with 3 significant figures, and we should go ahead and change it to scientific notation because, you know, that's what scientists like to do. 5.66 times 10 to the 3rd kilojoules. All right, our next equation. Once again, it gives us a mass of liquid hexane. It undergoes combustion in a bomb calorimeter. Here's our temperature change. Find the change of energy for the reaction. So first we're going to do Q of the calorimeter, which is equal to the specific heat of the calorimeter times the temperature change. Specific heat is 5.79 kilojoules per degree Celsius, and our temperature change is 38.13 minus 25.87, 12.26. I subtracted the bigger one from the smaller one from the bigger one. Now I'm going to multiply that by 5.79. and I get 70.9854. I'm not worrying about sig figs yet. Now that is the energy for that partial mole. Okay, so what we want to do is figure out what it would be for the whole mole. Okay, so we're going to divide it by the partial mole that we had. We had 1.550 grams. Hexane's molar mass is 86. So we're going to take 70.9854 divided by 1.55 divided by 86, and we get not the right answer. Let's try that again. This answer is 0.018023. Now I'll go 70.9854 divided by 0.01823, and I get 3,894 kilojoules. 3.89 times 10 to the third kilojoules, and it's a negative because remember this is going to be equal to the Q of the reaction. So this is a negative number, so those are negative numbers. So does that work? Yeah, it's pretty close to this guy. Except for what's he missing? He's missing the negative. So really that's the right answer there. These are right out of that online book. All right, the third one throws us a little bit of a curve. This time we know what the energy change is. We know that it's equal to negative 391 times 10 to the third because we just calculated it up here. All right, so we need to figure out what we have a new bomb calorimeter we're going to use. We know that we have this energy, and it tells us we have 1.55 grams of toluene. So we first need to change that to moles. 1.55 grams divided by, this is a different chemical, so I don't know why I pointed to the one above it. It has nothing to do with that one except for it's the same number. Toluene C7H8, 92. So we have 0.016848 moles. Okay, so that would be if you have a whole mole. No. Yeah, this number is if you have a whole mole. We don't have a hole in the mole, we have this part of a mole. So we're going to multiply those together. 16848. And we get 65.875 kilojoules. So this, and these are negative numbers, this is the energy. This is analogous to what we calculated up here. Okay? We're solving for the energy of the bomb, and this is the energy of the calorimeter. Okay? So we're going to change that to a positive, 65.875. This is Q calories. That's going to be equal to the specific heat times the temperature change. The temperature change was 37.57 minus 23.12. Divide both sides by 14.5. The specific heat would be 14.56 kilojoules degrees Celsius. Okay? There's not actually one of those in the problems. All right, this should set you up for the next set of problems. There's two of them. They're both like this guy. Okay? So, go get them, Tiger.